So we're going to talk about chemical equations and representing then a chemical reaction through them. So earlier in the quarter we talked about chemical changes, when we chemically recombine pure substances or break down compounds into pure substances to make something completely new. And in chemistry we represent that, we tell the story of that through a chemical equation, as you can see here. And I'd encourage you, as we're practicing balancing chemical equations or writing chemical equations, to also practice your naming rules, which we just learned. For example, this chemical equation here has a number of things that we could probably name. So the chemical equation is essentially the story of the chemical reaction that we're telling. We're saying this thing broke down into this, or these two things recombined chemically to make this new thing, and this is the way we represent that. And there's some language about it that you're going to want to be familiar with. So for example, we call substances that are written here before the arrow, we call these the reactants. And then we have this arrow that you can read as like becomes or yields to, or something like, maybe if you know it's decomposing, you can say decomposes to, but it's something along the lines of becomes. So these two become these. And then the stuff written after the arrow then are our products. And then you can see that we also often include some additional information, such as the state of our reactants and products. And you can have one or more reactants, and that's the same for products too. So here we have the state written there in the little parentheses. We have this is solid, this is aqueous, it means dissolved in, and then here liquid, and then our gas. So if I were going to then read the story of this chemical change, this chemical reaction, I would read it solid calcium carbonate plus or reacts with hydrogen chloride, aqueous hydrogen chloride, which would also be called hydrochloric acid, just as an FYI, yields or becomes aqueous calcium chloride, see I'm practicing my naming, plus water, plus carbon dioxide gas, or and. You'll notice that we always use pluses. If something's lost, we don't show it with minuses. That's just kind of not how we tell the story. And yeah, I lost my train of thought there. I hope it wasn't important. There we go. Another thing you might notice here is we have this number in front, and this number is the key to balancing the equation. The subscripts here they're the thing that help us understand the chemical formula, either the number of atoms in the molecule, like here with our water molecule, or the ratio between the cations and anions here in our ionic compound. The number in front acts as a multiplier to multiply everything after it, so that we're balancing, because matter can't be created or destroyed. So if I have something over here, I have to have that same number over there. So we're going to do some practice, and we're going to mix both. We're going to be practicing, and we're going to then also be throwing in a couple additional objectives for identifying some really common reaction types. So we're going to mix those two. We're going to practice and identify some reaction types. So practice and type of reactions. So starting here with how hydrogen gas and oxygen gas can react to make liquid water, you can see here that we would classify this reaction type as a combination reaction. And I like that. It makes sense. We have two or more products that combine into one. So combination. The reaction name really makes sense. So when we go to balance this, let's look at it first actually through like a modeling kit. So the same reaction, I'm saying oxygen gas, or hydrogen gas, my hydrogen's trying to roll away on me. Hydrogen gas reacts with oxygen gas, so I have my models, representing a little bit the Lewis structure, to make a water molecule. So this plus this should yield that. But you can see that if I were to actually demonstrate this, if I was going to start popping them apart to demonstrate that chemical reaction, I'm going to end up with an extra oxygen atom that doesn't get incorporated into my water molecule, which is a problem. Where did it go? So that's where we're balancing, because this can't quite occur. I'm going to need more of the either reactant or product in order for that to actually occur. Now there are several, there's balancing chemical reactions is in some ways just kind of a trial by fire. I would recommend using pencil, but I am going to share with you a few strategies that you can use and that you might find beneficial. And sometimes they're really simple and straightforward and you can see it right away. But sometimes they can be more complicated, and they're more complicated for chemists with advanced degrees. Sometimes it really is about like trying it out. So I will share with you just a few strategies. I'll move my notes page a little, sorry. First of all, it's okay to skip one if it's being tricky. If you're trying to balance something and it's not working, you can kind of skip it, and sometimes by moving on and balancing something else, you might find that it also gets balanced. Another strategy is save hydrogens and oxygens for last. They tend to be more likely to be in a lot of different locations throughout the chemical formulas. That doesn't work here because we only have hydrogens and oxygens, but you can definitely use that as a strategy. Another thing is the coefficient, the subscript on one side can often act as the coefficient on the other. So like this number could potentially become the coefficient then on the product side, and then you can just try it and then see how it goes. Hold on one sec. My throat's getting itchy. Another strategy that a lot of people will use is to create a table for keeping track of the number of atoms on your reactant side versus your product side. So I'm going to show you how that kind of table would work. I have reactant and I have product. You could also, do it right under here under the arrow. And then I'm going to write the element symbol for everything I have to keep track of. I have to keep track of only hydrogen and oxygen in this particular example. So on my reactant side, I have 2 hydrogen atoms. And I'm using that little subscript there. I have 2 of them. And you can see here in my model, 1, 2. And I have 2 oxygen atoms, 1, 2. On my product side, I have 2 hydrogen atoms, so those are technically balanced right now. But I only have 1, and you can see it here in the formula, and also here in my model, I only have 1 oxygen atom. So they're not balanced. We want all these numbers on the reactant side to be the same as our product side. So we want to have the 2 hydrogen atoms both before the reaction occurs and then after the reaction occurs. Those numbers need to be the same. So I can see here that my problem starts off right here. So the easiest way to make this a 2, or to balance these, is to make this a 2. And I do that using coefficients. We talked in class, you can't use a subscript because you're going to change the formula. You have to make sure that formula is written. So essentially, I'm saying 2 water molecules are going to be formed. So that changes my oxygen now. I now have it multiplies over. The coefficient multiplies over to the oxygen, or you could see here in the model, I have 2 oxygens, but look at my model kit. Look at my little model products over here. I have 1, 2, 3, 4 hydrogens, and I can see that here as well because that coefficient in front multiplies everything after it. So I now have 4 hydrogens. So I've created a balancing problem for hydrogens. So how do I get this number then to be 4 hydrogen atoms when it started off as 2? I need 2. I need another hydrogen atom. So 2 hydrogen molecules, sorry I used the word atom and molecule incorrectly there, 2 hydrogen molecules can react with 1 oxygen molecule to create 2 water molecules. And now, when I do that, when I consider that I have 1, 2, 3, 4 hydrogen atoms, I have 4 on this side and 4 on that side. That's balanced. And then 2 on this side, 2 oxygen on my reactant side and 2 on my product, and that's balanced. And so I've used, for this particular combination reaction, where I am combining. So you'll see I have multiple versions of my product, but I've combined my reactants into one product, and so it is a combination reaction. Now I'm going to sweep all these away. So those are, a table can be a useful strategy. You don't have to use a table. I'll be honest, I only use a table if I get stuck. If I can't intuitively figure it out pretty quickly, then I go to a table. So that first one on the copper to copper lab, I use a table. So moving on to another example. So this particular reaction, whoops, it's on the back. I did not realize that. So we have essentially the opposite. Oh, my little delta moved. We have the opposite of a combination, which is a decomposition. So a combination means we have one or more products that we're putting together. A decomposition means we have one reactant and we're breaking them apart into simpler products, sometimes even just their elements. You know, sodium chloride can be decomposed to sodium and chlorine. This little funny triangle here is supposed to be right here. Got moved around a bit, sorry about that. Ignore that. But I included it to show sometimes above that yield arrow we'll put special reaction conditions. Does this need a catalyst? Does it only occur in an acidic environment? You'll see a little H+. And here, our little delta here means heat. And sometimes you'll even just see the word heat. And you don't necessarily have to worry about that. But when remember, we're telling the story of this particular reaction. This reaction might look a little bit similar to what we did in the copper to copper lab when we took copper hydroxide and heated it into copper oxide in water. So it's a similar kind of reaction. So let's go through then and balance. First we want to ask ourselves, is this decomposition, is a vocab word for us, decomposition reaction balanced? And I can see right away it's not, because I have a different number of aluminums on the two sides. So this is one where choosing something other than hydrogen and oxygen is often a good place to kind of start. So we'll go ahead and solve with a table. Obviously you can pause and solve it yourself and just compare in the end if you'd like. We have aluminum atoms to keep track of, oxygen to keep track of, and hydrogen to keep track of. So on my reactant side, whoops, did the thing I was just about to tell you not to do. Ha ha ha. I have one aluminum atom. So this 3 here does not apply to the aluminum. It only applies to the polyatomic ion, the hydroxide ion. So I have solid aluminum hydroxide decomposes to aluminum oxide and water. But the 3 does multiply to those in between, but not the aluminum. So I have 3 oxygens and 3 hydrogens. Then on my product side, using my subscripts, I have 2 oxygen atoms over here. And this is really easy to do. You got to notice that you have oxygen in 2 places. I have oxygen in both the aluminum oxide and the water molecule. So I have a total of 4 oxygen atoms and then 2 hydrogen. Now, because hydrogen and oxygen can often cause me some grief, I do like to save them for later, because sometimes by balancing something else, they'll get balanced in the process. So I'm going to start with aluminum, plus aluminum kind of presents an easy way to get to 2. I have an imbalance in my reactants and products. So I'm going to put a 2 over here in front of my aluminum hydroxide substance. That 2 multiplies over then to my aluminum, and I now have 2 aluminum atoms considered in my reactant side. Sorry. Now this 2, however, multiplies this 3 to 6. So that's then going to say, no, I don't have 3 oxygen atoms, I have 6. I don't have 3 hydrogens, I have 6. So I've become further imbalanced on my reactant side. So next, I have to decide, do I want to focus on hydrogen or do I want to focus on oxygen? And I'm going to choose hydrogen. And the reason I'd like to choose hydrogen next to try to balance is because hydrogen is only located in one place on my product side, whereas my oxygen's located in 2. Again, going with maybe oxygen will resolve itself if I focus my balancing efforts on hydrogen. So I have 2 hydrogens found in this water molecule on the product side, which came from hydrogens here, and I have 6 over here. So the way to get to 6 then, to make those number equals, would be to use the multiplier, the coefficient of 3 in front. So 3 water molecules are coming out. So that would then make this 6. And if you look, you'll notice I have fixed the oxygen problem as well. I have 3 oxygen here, and then now I have 3 oxygen here, and I have balanced the aluminum, the oxygen, and the hydrogen on both sides of the reactants and the products. And again, this is a decomposition reaction because I have one reactant that's breaking down into some simpler products, maybe even its elements. Next. So this is a reaction type that you saw in the lab, and that is called a single replacement or single displacement. I tend to say single displacement. I think that's probably more along the lines of how I was taught, but I believe your book calls them single replacements. I also call them the cutting in reaction. So if you look closely at what's going on here, we have an alone element, a bachelor. And then we have 2 substances, nickel and the polyatomic ion nitrate. Kind of think of them as like dancing with each other. And on this side, we've had an exchange of dance partners, or a cutting in. Aluminum is cutting into the reaction. Excuse me, can we have this dance? And then we end up with nickel, jealous and angry. And this reaction was actually the final step of our copper to copper lab when we add solid zinc to copper sulfate to get our copper back, and we end up with an aqueous solution of zinc sulfate. So you have experienced a single replacement reaction or a single displacement reaction already. So there's another tip for this kind of problem, in that when we have a polyatomic ion on your reactant side, look on your product side to see if it stayed together or not. And by that I mean, do we have NO3 over here, and is it still NO3 over here? Because it might not. It could decompose and change and be all over the place. You've seen some reactions like that in lab. But if it stays together, rather than track our nitrogen and our oxygen, we can just keep track of the nitrate particle as a whole. So when I go to do my table, and I'm looking at my reactant side versus my product side, I'm going to keep track of aluminum, I'm going to keep track of nickel, and rather than saying, now I'm going to keep track of nitrogen and now I'm going to keep track of oxygen, I'm going to keep track of nitrate. I'm going to keep track of it together because it stayed together, and that simplifies my process a little bit. So I have 1 aluminum atom on my reactant side and 1 on my product. I have 1 nickel and 1 nickel. Nice, we're doing great. I have 1 nitrate right here. Again, I'm going with the whole thing. I'm treating the whole thing as a single particle because it is actually kind of what it is. And over here, I have 3. So my reaction isn't balanced yet. Now, I like polyatomic ions when they stay together because they're a good place to begin. If you have a polyatomic ion on both your reactant and product side, I'd recommend starting there. Now, really, in this case, it's the only logical place to start anyway. So if I have 3 in my reactant side, I'm not going to come over and do parentheses and 3. I'm not going to do that because that would be changing the formula. I'm going to put a 3 in front of the nickel nitrate substance here, and that's going to multiply my nickel to give me 3, and it's going to multiply my nitrate. Now you have to be careful here. You don't want this 3 in terms of going, I don't want to think, oh, I have 9 nitrate. That NO3 is what nitrate is, so you only have 3 nitrate. Now that happens to include 9 oxygen atoms, but we're keeping track of the individual particle. Now, from here I can see the only thing left to balance is nickel, which is all by itself and fairly straightforward then to balance. And now everybody, I have the same mass of each element on my reactant side as I do on my product side for this single replacement or single displacement, or the cutting in reaction. That's just what I call it. Don't tell anyone else that. Similar to the single, we can also have a double displacement reaction, double displacement or double replacement, or the wife swap, or the switching dance partners. So in some ways it looks kind of similar. If we look really closely to what's happening here, you can see that our sodium was with our carbonate. So if I were going to read this reaction, I would read it: aqueous sodium carbonate reacts with aqueous aluminum chloride, to yield or create aluminum carbonate plus aqueous sodium chloride. So when you look here, you can see that sodium, if you want to think of it like in terms of dance partners, is dancing with carbonate, and aluminum is dancing with chloride. But on this side of the reaction, the product side, they've exchanged who they're dancing with. So instead of being with aluminum with the negative chloride ion, it's with the negative carbonate. It's still an ionic compound. It's still a positive attracted to a negative, but it's switched the dance partners. And our sodium is now dancing with our chlorine for this double displacement reaction. We're going to talk more about these in the future because they can be potentially pretty cool. So let's solve this with a table. Again, you do not have to. This is just one particular method I want to show you. And I have sodiums to keep track of. And that's a polyatomic ion, and I know that because I study my polyatomic flashcards every day. And I see that I have it on my product side as well, and that it didn't break up into any other products. So I'm going to keep track of it as a carbonate. I also have aluminum, and I have chloride or chlorine. On my reactant side, I have 2 aluminum, 1 carbonate. I have to make sure I think of this as 1 rather than accidentally writing the 3. I have 1, I think I said that wrong. Bear with me. 1 aluminum, 2 sodium, and then 3 chlorine. On my product side, I got to jump down. I got to make sure I'm the right one. 1 sodium, 1 chlorine, 2 aluminum, and 3 carbonate. 3 multiplies, it goes to this whole thing. I have 3 of those carbonate atoms. So where should I begin? Well, as I said before, I like to start with polyatomic ions if they stay the same on both sides, because I think they tend to solve the balancing of other things pretty easily. So since I have 3 carbonate ions on this side, I need to use a coefficient to give me 3 on that side. That changes this number on my reactant side to a 3, but you'll notice it messed with my sodium. I now have 6 sodium ions on this particular side because that 3 multiplies that 2. So let's go ahead then, because my sodium is just 1, the only way to get it up to 6 is to put that 6 coefficient in front, and that multiplies to the sodium, and it also multiplies to the chlorine, bringing it up to 6. Now the relationship between 6 and 3, how can I get to 6 from 3? Well, 6 divided by 3 is 2. So I'm going to put a 2 then there in front of my aluminum chloride, which multiplies my chloride then to 6, and without ever having to put any thought into how to balance aluminum, balances my aluminum. And I have the same number of atoms for each element on my reactant side as on my product side for this double displacement reaction. So there's one more that I want us to do together, and there's no reaction type here, not that it's not a reaction, but it's a reaction type we're going to talk about later in the quarter. For simplicity, this is, we call this a combustion reaction because we have ethane burning in the presence of oxygen to make carbon dioxide and water. But the reaction type is not the big focus here. I want to show you one more technique that some people might use for balancing an equation. So let's start kind of based on where we've been, and then see the problem that can happen, and then go, okay, what might be a strategy to address that? So I have my reactant and my products. I have carbon, hydrogen, and oxygen to keep track of. On my reactant side, I have 2 carbon atoms. On my product side, I have 1. On my reactant side, I have 6 hydrogen atoms. On my product side, I have 2. And I'm already starting to think about some multipliers that would work, some common mathematically related numbers. On my reactant side, I have 2 oxygen atoms, and I have 3 oxygen atoms here on my product side because I have 2 in my carbon dioxide and 1 in my oxygen. Now, this problem presents a unique challenge in that as we start to balance, you're going to notice that this number always is going to end up being even. So when we start to balance it, we go, okay, let's start with our carbon, since hydrogens and oxygens are kind of a pain, right? So we'll start with carbon, and I want to get 2 on this side to make it match. So I now have 2. But I've multiplied my oxygen as well. So that is 4 oxygen plus this one. So I have 5. Now look at the problem I'm generating here. I have a little bit of an issue. I have what's always going to end up being an even number on my reactant side, but I have right now what's always been an odd number on my product. And if I keep trying, you'll see that that's going to keep happening. So let's try to balance my hydrogens. I have 6 over here, and I have H2, so I want to get a multiple, something that times 2 will be 6. Well, that's 3, so let's put that coefficient in front, and that changes my hydrogens to 6. Oh good, I'm almost done, right? Well, how many oxygens do I have now? I have 4 over here, 4, 5, 6, 7. How am I going to, using something that's always going to end up being an even number, because anything times 2 is going to be even, get to what seems to be constantly an odd number on this side? And there are several different strategies for this, and one is trial and error. Keep trying numbers until you get to one that works. Another strategy is to add an additional step, which is go ahead and use a decimal, use a fraction to start. So for example, if I put 3.5 here in front of my oxygen, 3.5 times 2 is 7, and they're now balanced. So you might be wondering, can you do that? No. I mean, technically this is balanced, but in general that's not how we balance a problem. We don't use half, but it helped me mathematically get there, because now what I'm going to do is I'm going to multiply the whole reaction by 2. So I've rewritten, I have the same thing again, but blank since I've written all over it. So 2, and my coefficient was 1. So 2 of this molecule, this is called ethane. We don't learn the names in 121 for this. 2 times 3.5 is 7. 2 times 2 is 4. And then 2 times 3 is 6. And this is the lowest, like the most reduced form for balancing the reaction that I can get. And if we look then in terms of what do we have 4 carbons on this side and 4 carbons on this side. We have 12 hydrogens on our reactant side. We have 12 hydrogens on our product side. And that tricky oxygen, which ended up being in so many different places, we have 14 on our reactant side, and we have, here we have our 8, and then our 6. We have 14 on our product side as well. So don't give me halves as your answer, but you could use halves to, if you can balance it with halves, then you take that additional step of multiplying each coefficient by 2. Now, if you have a situation, and I don't have an example of this, where you've balanced and you find at the end you realize that all of your, like you've used these coefficients, you can reduce that because they're all divisible by 2. So when we balance, we do go with the lowest, the most reduced form for balancing that reaction. But this is a method that you can use with these half and then multiply by 2 in the end for some of those trickier problems. If you're looking for extra practice, and I can't say enough, practice makes permanent. It's what moves information from your short-term to your long-term memory. I'd really encourage you to look at Canvas. There's some Canvas worksheets, like just dozens and dozens of balancing reaction problems. And there's also some videos of me just going over even more problems for extra practice. And you can pause those videos and solve them and then check your work. And as always, if you're struggling, come and talk to me. I'll see you guys soon.